And today we have with us Dr. Malay Bhatt, who is an associate professor in the DDU University Nadiad. So, sir is having very good experience in the subject of theory of computation, and today sir is going to share their knowledge about the context-free grammar for the context-free languages. So, student, as you know that it is our this concept is also part of our syllabus. Okay, so please do interact with sir. Please listen to the sir carefully. Sir is going to provide you very good knowledge and very good understanding about the context free grammar for the context free languages. So I request Dr. Malabat sir to please start the session.
Hello students, good afternoon to all. So today we'll see how to write context-free grammar for the context-free languages. And during presentation also we'll define what is a context-free grammar as a term. But we'll start with first how to write a grammar for some simple languages, and then slowly we'll move it towards a definition of a context-free grammar, and we'll go for very complex and interesting examples. So as you are aware, in theory of computation, the main thing is Chomsky hierarchy. This Chomsky hierarchy is about different grammars which are used in the theory of computation. You might have studied a type 3 grammar which is known as regular grammar, and for which we are using finite automata as an abstract machine to accept the regular languages. Our focus over here is on type 2 class of grammars, which is known as a context-free grammar. And as you are aware that we cannot do any comparison in finite automata because we don't have any memory associated with finite automata. On the other hand, in context-free grammar, we are using abstract machine as push-down automata, which is using a stack as a memory to check whether a given string is accepted by the machine or not. So the automata which is associated with context-free grammar is push-down automata. And type 1 grammar, a context-sensitive grammar, with which the associated automata is a linear bounded automata. And with type 0, which is known as unrestricted grammar, it is associated with a Turing machine. So now let us start with our first example, and we are taking a very simple grammar first. So here you can see that I am writing here that S gives small a, capital S, and B. So we can say that we have a variable S, or we can say a non-terminal S, which can be replaced with small a, capital S, small b, or we can say A, S, B. So this A and B are known as terminal symbols of the grammar. Symbol S, which is known as a non-terminal symbol of the grammar. And for non-terminal S, we have two different alternatives here. Either I can replace non-terminal S with ASB, or I can replace non-terminal S with null. So we have two different alternatives, and we are free to use any of these two alternatives as per our requirement. So basically, this non-terminal S we are replacing with ASB. So I can say I am recursively applying this rule so that I am able to replace S with ASB any number of times. Or if I want to terminate the process, I will replace S with null. So here we have two options for non-terminal S, and these two alternatives are known as two rules of the grammar. Normally we'll use symbol S to represent starting symbol of the grammar. Now, using a grammar, we can derive any string. So here I am deriving the string AABB, as you can see here. I am deriving a string AABB. So to derive this string, to generate this string, we'll start with a non-terminal S, starting symbol of the grammar. Then I want A and B as a string. So I will replace non-terminal S with ASB. So I am replacing S with ASB. Now my requirement is we want two occurrences of A and two occurrences of B in a specific order. So now to achieve that goal, we are replacing again non-terminal S. We are replacing again non-terminal S with ASB, as you can see here. So now we have two occurrences of A and we have two occurrences of B. Now to complete the process, to terminate the process, I will replace non-terminal S with a symbol null. So this represents a null symbol. This is representing a null symbol. So to terminate the process, I will substitute this null for this capital S. So we'll get the string AABB. Now similar to that, we'll try to generate another string, and that is triple A triple B. So to generate this string, we'll start with starting symbol of the grammar S. Then because I can replace S with ASB, I will replace S with ASB to get A and B. Recursively, I will replace capital S with again ASB. So we'll get two occurrences of A, S, two occurrences of B. One more time, I will apply rule for non-terminal S and will write S is replaced with ASB. So now you can see we have three occurrences of A and three occurrences of B. So at last we'll put null for the non-terminal S to terminate the process. So this process of generating a string. This process of generating a string is known as a derivation. We are deriving a string. This process of generating a string is known as a derivation. The symbol S, which is represented by capital letter S, is known as non-terminal. We are representing terminal symbols like A and B with small letters. And when we are replacing S with ASB or S with null, these are known as rules of the grammar. These are the two rules of the grammar. So now if you observe the pattern over here, you can easily identify that which kind of language it represents. As you are aware, language is nothing but a set of strings. When we define a language, it is nothing but a set of strings. So here you can see we can derive a null string directly. I can derive a null from S by replacing S with null using direct one rule. I can only derive AB. I will replace non-terminal S with ASB and then I will put null for non-terminal S. So you can see that we are generating this set of strings, a null, then AB, then double A, double B, triple A, triple B. So we have all these strings. We have infinite such strings we can derive using this grammar. So if you observe all these strings, you will find that they are following a certain pattern. All these strings are following a certain pattern. So if I represent, I can say this grammar represents the language L is equal to A raised to N, B raised to N, where N is greater than or equal to 0. Because if you put N equal to 0, you will get A raised to 0, B raised to 0, which will give you null. When you consider N equal to 1, you will get A raised to 1, B raised to 1, which gives you AB. If I take N equal to 2, you will get A raised to 2, B raised to 2, which is giving you AABB. So you can see that we are generating all these strings using this grammar. So basically, this grammar represents the language a raised to n, b raised to n, where n is greater than or equal to 0. Instead of terminals a and b, if you take a as opening parenthesis and b as closing parenthesis, and if you write a grammar like this, s gives opening parenthesis, s closing parenthesis, and s gives null, then you are able to derive this kind of strings, opening and closing parenthesis. Then we have a nested pair of parentheses. So you can derive all this if I take terminal symbols as opening and closing parentheses. So this is a very simple grammar which is giving you a hint that in a grammar we have a non-terminal, we have a terminal symbols. So the terminal symbols are those symbols which cannot be replaced with any another symbol. You don't have alternative for the terminal symbols. Or in other words, we can say that we cannot replace a terminal symbol with any another symbol. And we have a non-terminal which can be replaced with another combination of terminal and non-terminal. So now with this simple example, I hope it is clear that how we can derive a string from the grammar, what is a non-terminal, what is a terminal, what is a production rule. So with this, now let us go for one more example. I hope there is no doubt in the first example. If you have any query, you can immediately ask so that we can discuss it more. And if you have a query, it is good, because if you clear your doubts, you will never make that mistake in the examination, because writing a grammar is an art. It is not that you randomly write anything and it becomes a grammar. So if you have any query that why we are not writing like this, you have to immediately ask. Okay, now let us take a second example. We have a language X belongs to AB star. X is an even length palindrome. So I hope you know what is a palindrome. If you read the string from left to right or from right to left, it will be equal. It is known as a palindrome. Like a null, so it is a palindrome. If it is taking AA, it is also a palindrome of length 2, because length 0 is null. Length 2 palindromes are AA and BB. Now further, if we consider even length palindrome, so in this AA, I am appending A on the left hand side and I am appending A on the right hand side. So if I read from left to right or from right to left, it will be equal. Similarly, if I append B and B, then also you can see that if you read from left to right, it is BAAB. If I read from right to left, it will be BAAB. So left to right or right to left, it is equal. Here also you can see that with null, when I'm appending A and A, it becomes AA. Similarly, when I'm appending B and B, it becomes BB. So when you are appending equal element on both the sides, then you are getting a palindrome, and you can apply that any number of times. So here you can also see that I'm applying B and B with the string AAAA. So we are getting again a palindrome BAAAAB. So you can see that we are generating this pattern starting from null. Just we are appending the equal elements. So we are getting AA. Then I'm appending B and B. So I'm getting one more palindrome. Then I'll append A. I'm getting one more palindrome. Last should be A. So you can see that we are getting a palindrome by appending the elements, equal elements on both the sides. And we are applying that recursively any number of times. So this is how you will get all the set of palindromes. For BB, if I append AA, we'll get ABBA. Then further, if I append B and B, we'll get B, ABBA, and B. So we are getting this set of palindromes. So now if I want to write a grammar, we know that we must have equal symbols on both the sides. We must have equal symbols on both the sides, and we have to apply that rules recursively. So here we are writing from starting symbol S, we are writing A as A. So we are appending A and A on both the sides. Similarly, we have B as B. So we are appending B on left hand side, another B on right hand side of S. So that is how we are getting the rule for this even length palindrome. Now we can use a derivation to derive any string. We'll start with S. Then suppose we want to derive this pattern ABBA. So from S we'll write A S A to get this A and A. Now to derive BB pattern, I will replace S by the recursive rule B S B and A. So I am getting this B and B. Now to terminate the process, I will write AB null BA because null is for termination, and finally we'll get the pattern ABBA. So we are able to derive the even length palindrome, which is equal from both the sides, left hand side and right hand side. Similarly, we can derive any another string using this simple rules. So if we start for another example, let us take AAAA. So from starting symbol S, we'll replace with ASA. Again, we want another set of A's. So I will replace S with A, S, A, and A. Finally, we'll put null. So we'll get A, A, A. So you can see here that we are able to derive any string using this grammar, which is very simple. So here we have three different rules. The first rule is, if we write the rules separately, first rule is A, S, A. The second rule is B, S, B. And third rule is S gives null. Or from S, we are producing null. So we have three different rules in this grammar. We have one non-terminal, a starting symbol of the grammar. We have two terminal symbols, that is A and B. So using this simple grammar, we can derive any even length palindrome. If I want to get only null, directly I can use the rule S gives null. So I hope it is clear. Yes, do you have any query in this second example? Okay, if you don't have a query, can you tell me, can I write like this? S gives AAS or S gives BBS. Can I write like this? If I do in this way, what will happen? Let us see. Suppose you want to derive a string ABBA. So we'll start with S. We'll get AAS because we want AA. Now you don't get AB because this rule gives us AA. We require AB in the beginning. So definitely we cannot write in this way, that we cannot put S at the end, because we are generating A on both the sides, on the left hand side as well as on the right hand side, to get the new strings. So we cannot write in that way. So yes, do you have any query in this example? Right? If you have any query, you can immediately ask, because we have to go for several complex examples. Because normally in DDU, we are having a lot of interaction during the session, that students are immediately asking that, can we write like this? Can we write like that? So that their doubts will be clarified immediately during the session. If you feel that, can we write like this? Immediately we can discuss that, is it true or false, and why we cannot write. Because it is very important to know that why the grammar is incorrect, right? Everything looks equal, but you should know that what is correct and what is incorrect. So now here, this is what we have done. We have derived the string ABBA. We have derived the string ABAABA by derivation process. We'll start with S. Then To get the A, we are writing ASA. We are getting this A and A. Then to get the B, we'll replace S with recursive rule BSB. And then to get the A again, we are replacing S with the recursive rule ASA. So by writing this simple grammar, S gives ASA or BSB or null. So basically this vertical line, a pipeline symbol, is indicating the or sign. We have three alternatives and you can apply any alternative as per your requirement to derive the required string. So this is how we can generate all the infinite strings of this even length palindrome language. Okay, now if I want to generate odd length palindrome, this doesn't generate odd length palindrome. So to generate odd length palindrome, can you suggest some modification which we can do? That what changes we have to do if I want to generate odd length palindrome? And I hope you know what is an odd length palindrome. You have to slightly modify this. Like this, ABA, or we can say BAB, which are odd length palindromes. Or we can say ABA. So you can see that we have to do some modification. I'm giving you a hint also that what changes we have to do. Right? So if you tell me, it will be good. Because more interaction means more clarity. That is the only thing which will work in this subject, theory of computation. You might have gone through finite automata and regular expressions, so you know this very well. Yes, can anyone give the answer? That what changes we require to achieve odd length palindrome? Even though your answer is incorrect, you can tell freely. No need to worry. If you know why you are incorrect, you will never do that mistake again in the external examination or in sessional
Sir,
examination.
we can add only A and only B.
Okay, so do we keep null along with it?
Yes.
Okay, what is your number? Can you tell me?
158.
Okay, so now let me tell you, you are almost correct. So what we have to do, that we'll add A and B, right, as a two different rules, right? We'll add A and B as two different rules in this. So we'll write like this. Now we are eliminating null from this because here the terminal symbol A or terminal symbol B will act as terminal symbols. It will terminate the process. Now if I put null along with this, then what will happen? It will allow me to generate a strings like this, which is a even length palindrome. If I replace S with null, I will get even length palindrome also. So here my requirement is we want to generate only odd length palindromes. So if we remove null from this rule, then and then it will allow me to generate only odd length palindromes. Because at last you have to replace S with either A or you have to replace S with either B. So as you can see some derivations here. From S we are having ASA, then for S non-terminal we are replacing with BSB, and then we have A at the last. So now to terminate the process, we don't have null here. As we don't have null here, we have to put A or B as per the requirement. So here we are putting A. So we are getting the pattern ABA BA. We are getting the pattern ABA BA, which is a odd length palindrome. Similarly, I can derive from S pattern like BAB. If I replace final last S with terminal A, or I can derive ABA if I replace the last occurrence of S non-terminal with terminal B. So to get the odd length palindrome, we have to do a slight modification. Just we have to replace null with A or B. Now if I want to generate a general palindrome, that is odd length plus even length, In that case, we have to append null with it. If I want to generate both odd length palindrome and even length palindrome, then we have to append null along with this rule. Okay, so now let us do more interesting examples. So now we have a new language. X belongs to 0, 1 star. Now our input alphabet is 0 and 1. Number of zeros in the string X is equal to number of ones in the string X. We want to generate a grammar for this. So now let us see some examples. That null is a valid string. Yes, because it has equal number of zeros and ones. Now what this grammar tells, that when we want to generate 1 0, we have to generate 1, so that there will be equality. So when I am generating 1 0, I have to generate 1 1. So now from this two examples, if I write a grammar, it will be like this. From S we'll get null. From S we'll get 0 S 1. So this will generate equal number of times 0 and 1. Now if I add one more example with this 1 0, this 1 0 has also equal number of zeros and ones. So if I want to generate this pattern 1 0, these two rules are not sufficient. So to achieve my goal, I will add one more rule with this. That is S gives 1 S 0. So now I can generate any of these strings. So I hope it is straightforward that how we can generate this. From S we'll put null, so we'll get the first string. From S we'll write 0 S1, a recursive rule, and then we'll put null, so we'll get 0 1. From S we'll write 1 S0, and then for S we'll put null, so we'll get 1 0. So you can see that we are getting all these patterns. Let us check for some more patterns. Can we generate that? So let me add one more pattern. We want to generate this pattern 0 1 1 0. So let us check that can we generate this pattern, or let us consider or let us check for this. So now if I try to generate this pattern, let us first focus on this 0 1 0 1. So now to achieve this goal, we'll start with S. Now we want 0 and 1. We want to generate equal number of times 0 and 1. So I will match first with last 0 1, because we have a rules like that. So I will write 0 S1. Now to get 1 0, I will replace this S with 0 1 S 0 and 1, and finally I will put null to terminate the process. So we have 0 1 0 1. So we are able to generate the string. Now let us check for another one 1 0 1 0. Now to generate this, we'll start with S. We'll write 1 S 0. So we are getting 1 0. Now to generate 0 1, I will replace this S with 0 S1 and 0. So last we'll replace non-terminal S with null. So we'll get 1 0 1 0, which is our desired pattern. So you can see that we are able to generate this pattern. Now we need to check, can we generate 0 1 1 0 from these rules? So that means we require a rule which generates equal number of zeros and ones. But here our rules are such that when we are generating 1 0, we are generating 1 1. So now if I try to match this 0 with 1 and 1 with this 0, then you can see that we have two rules 0 1. We have another rule 1 0. But here what we require a concatenation of these two rules. We require concatenation of these two rules to achieve the goal. Similarly, if I write 1001, which is also having an equal number of zeros and ones, and it also shows the concatenation that 10 is there and we have a 01 is there. So now to achieve the goal, what we'll do is we'll add one more rule in this grammar, and that is S gives SS. So now because of this new rule, you are able to derive the strings. I will replace S with SS. Now for this S, we have 0S1 and S. Now for the first S, we'll put null, so we'll get 01 S. Then for the second S, we'll write 1 S0. Right? At one point of time, we have to always consider one non-terminal. We cannot consider together. And we have to go always from left to right. We have to always go from left to right. So here we'll get 0, 1, 1, 0. Similarly, for the second one, we'll start with S. We'll replace with SS. Then 1 S0 S. We'll replace S first S with null. So 1 0 S. Then 1 0. I will replace this S with 0 S1. Then 1 0 0 S1. So we'll replace S with null. We'll get 1 0 0 1. So now if you look at this, now any combination, because we have checked all the combinations of length 4. First we will check length 0, then length 2, then length 4. All combinations we have checked here, which is having an equal number of zeros and ones. So by going through all these examples, it is clear that it is a valid grammar, which will give the final answer. So our final answer is only this, that we have S, which is replaced with 0 S1 or 1 S0 or SS or null. So if you consider this, this is your final answer with all the rules. Yes, so do you have any query in this example? Or if you want to test any string which you want to derive, if you want to derive any string, you can tell. We can check here right now also that we want to derive a particular string. Right? If you have any query. Okay, so let us go for more interesting examples. X belongs to 0, 1 star. Two middle symbols are always equal. So now we want a specific grammar in which middle symbols are always equal. So this means we have two different options. Either two middle symbols will be 0, 0 or two middle symbols will be 1, 1 because X belongs to 0, 1 star. So now once we are getting two middle symbols equal, there is no rule that what is on the left hand side of it, what is on the right hand side of it. But it must be two middle symbols. That means we have to append some symbol over here. At the same time, we have to append symbol on the right hand side so that this 0, 0 will be in the middle position. If I append one symbol on the left hand side and if I do not append a symbol on the right hand side, it will not give this 0, 0 and 1, 1 in the middle position. So we have to append any symbol, but it must be equal. So we have one option here. I can append 0 and 1. I can append 1 and 0. Still it will remain in a middle position. I can append 1 and 1. And I can append 0 and 0. So you can see that if I put these two middle symbols here, we are getting all the strings of length 4. Similarly, for this 1, 1, I will append 0 and 0. I can append 0 and 1. I can append 1 and 0. I can append 1 and 1. And here I will put 1, 1. So you can see that still this 1, 1 is in a middle position and two middle symbols are equal. So that means what? This will give us a hint that the rules like this, that when you append 0, we can have 1 on the other side. When you append 1 on left hand side, 0 can be on another side. When you append 1 on the left hand side, another 1 can be on the right hand side. When I append 0 on the left hand side, another 0 can be on the right hand side. And at last, to terminate the process, we have to replace the non-terminal with 0, 0. Right? We will replace the non-terminal with this 0, 0 to terminate the process. So from this, if I can write something like this. From S, I will replace with A. So this non-terminal A indicates that my middle symbol will be 0, 0. Or we have a second option. I will replace S with B when my middle symbol is 1, 1. So we have two different paths, and these two paths are different. Either you will go with A when your middle symbol requirement is 0, 0, or you will go with B when your middle symbol requirement is 1, 1. So now, after that, what we have to do, from A, I can generate 0 on left hand side and 0 on the right hand side. I can generate 0 on left hand side, 1 on the right hand side. I can generate 1 on the left hand side, 0 on the right hand side, 1 on the left hand side, and 1 on the right hand side. And at last, I will replace with 0, 0. So now you can see that we are covering all the rules: 0, 1, 1, 0, 1, 1, and 0, 0, all the combinations on the left side and the right side. And at last, to terminate the process, we are putting 0, 0. Similarly, if I want to write for B, I can write like this. For B, we'll write 0, B, 0, then 0, B, 1, then 1, B, 0, 1, B, 1, and 1, 1. So you can see that we have two different alternatives here, and we can derive any string. So let us derive some strings using this grammar. So why we have two different paths? Because either you require a middle symbol as 0, 0, or you require a middle symbol as 1, 1. So we have two different paths here. Let us derive one string. Let us take a string as let us put 1, 1 in between. Then we have 0, 0, 1, 1. Let us derive this string. So now we'll start with a starting symbol of the grammar S. Now we want in the middle position 1, 1. So as we want 1, 1 in the middle position, I will select the path as B. So I will replace S with B because I want 1, 1 in the middle position. Now, once it is done, my requirement is 1 and 1. So I will replace this B with 1, B1. Then my requirement is 0 and 0. So I will replace this B with 0, B, 0. And once we are getting the two middle symbols left, we'll replace this B with 1, 1. So we are getting this pattern 1, 0, 1, 1, 0, 1. We are getting the pattern 1, 0, 1, 1, 0, 1. Now similar to that, if you want to derive a string having two middle symbol as 0, 0, we can write like this. Suppose the string, let us take a string 0, 0 in the middle, then 1, 0, and 0, 1. Suppose you want to derive this. So as we require 0, 0 in the middle, we'll replace S with A, then 0 and 1. We'll replace non-terminal A with 0, A1. Now I will replace this 1 and 0. To get this 1 and 0, I will replace this A with 1, A0, and 1. And at last, I will put 0, 0 to get two middle symbols equal. So this is how we are able to derive the string. So if you look at this, you can see that we have three known terminals here, right? If you write down the known terminals of this grammar, we have three in this: S, A, and B, because you can replace S with A or B. You can replace A with different alternatives. We have 5 alternatives for non-terminal A. Similarly, for non-terminal B, also we have 5 alternatives. So this is our final grammar. If you look at this, so I hope it is clear. So this is the final answer, that we are getting two middle symbols always equal with this three different non-terminals. So do you have any query in this? You can ask that. So this step is not clear. So can you explain with more example? Then we can discuss it. Okay, so let us go for the more interesting examples. So here we have first, middle, and last symbols are equal. Now we have one more modification, right? We want first, middle, and last symbols equal. So definitely when we have three symbols equal, the length of the string will be 3 or more than 3. So if we write, we have the first symbol, last symbol, middle symbol, and the last symbol. All three are equal. Okay, let me write more separately so it will be more clear. So it is like this: the first, middle, and last. These three symbols are equal. Now along with that, to achieve this goal, here there is no restriction. So here I can put 0 and 0. I can put combination of 0 and 1. I can put combination of 1 and 0, or I can put a combination of 1 and 1. So you can still see that the first, middle, and last all are equal. Similarly, if I consider, I can write for 1. We have the first symbol can be 1, the middle symbol is 1, last symbol is also 1. And here there is no restriction, so I can put 0, 0. I can put 1, 0. I can put 0, 1, or I can have 1, 1. So still you can see that first, middle, and last symbols equal. So definitely here, when we are terminating the process, right, we have to put at last the symbol 1 if first and last symbols are 1. If the first and last symbols are 0, middle element should be also 0. So from this, what we can say, that we have again two different paths. The first, if it is 0, last will be definitely 0, and middle symbol will be also 0. So now to achieve the goal, we have two rules here. From the S, if the first symbol is 0, definitely last symbol will be 0. If first symbol is 1, last symbol will be also 1. You cannot have a different symbol. So this is how we are fixing the positions, right? From S, we have 0, A0. If first is 0, last is 0. From S, if first is 1, last is 1. And now, once you are replacing S with 0, A0, or you are replacing S with 1, B1, you are applying that rule only once. It is not a recursive rule. It is not a recursive rule. You cannot apply that infinite times. Now for non-terminal A, as you can see that once you are fixing the first and last position as 0, the middle element will be 0. So we have 0. Now on two different sides of this 0, because middle element is always 0, so we are terminating A, which is a middle position, with 0. Now on the other side, left and right side, it can be any combination. You can see 0 0 0 1 1 0 1 1. Any combination is a valid combination. So because of that, we'll write 1 A1 1 A0 0 A1 and 0 A0. So now you can have any valid combination, 1A1 1A0 0A1 0A0, and at last you will terminate this A with 0. So it will be in the middle position. It will be in the middle position. And similarly for non-terminal B, we have the same approach. The middle symbol will be always 1, and we have all the options valid. So we can write 0 B0 0 B1 1 B0 1 B1. So we are getting this grammar. So now using this grammar, I can derive the string. So let us derive any string using this grammar which we have generated. So let us start with S. Suppose you want to derive a string. Let us take a string 0 0 0, and here let us put 1 1. So first, middle and last equal. So we'll start with alternative of S, that is 0 A 0. So we are getting the first and last position 0. So now we have non-terminal A, so we cannot apply any rules starting with B. So only rules which are from non-terminal A we can apply. So now I will replace A with, I will replace this A with 1 A1. So I replace A with 1 A1. And now to get the final middle position, we'll replace A with 0. So we have final string as 0 1 0 1 0, where first, middle and last symbol equal. So this is your final grammar. This is rule 1. We can say rule number 2. We have rule number 3. Or if you want to combine rule 1 and 2, you can also write like this. That is a more straightforward approach. We will replace S with 0 A0 or 1 B1. So now we have first, middle and last. All three symbols are equal. So I hope it is clear. There is no query in this. Okay, so now we have one more example. We have L is equal to A raised to N, B raised to N, C raised to M, D raised to M, where Mn greater than or equal to 0. So if you look at this language, it is similar to what we have done in the first example. If you recall this, A raised to N, B raised to N, N greater than or equal to 0. So this is similar to that, but there is a minor change. So I can say that for this language L, we have two languages inside it, and there is a concatenation of two different languages. Here our L1 language we can say is A raised to N, B raised to N, and our L2 language is C raised to M, D raised to M. And M and N both are greater than or equal to 0. So now for the L1 language, for this L1 language, I can write a grammar like this. A, S1, B or null because n is greater than or equal to 0. And for the L2 language, I can write a grammar. S2 gives C, S2D or null. So why we are writing for S1 A, S1 B? S1 is the starting symbol of the language 1, L1, and it is a recursive rule. We are producing equal number of times A and B, A on the left hand side and B on the right hand side. And similarly for the L2 language, we are using a non-terminal S2 as a starting symbol, and we are writing S2 gives C, S2D. So we are producing C and D equal number of times, C on the left hand side and D on the right hand side. And to terminate the process, we are putting null because n is greater than or equal to 0. So n can be 0 also. Similarly, value of m can be also 0. So now to achieve the final goal, because we want a grammar for the language L, which is a concatenation of two different context-free languages, So now for that, we'll add one more rule in this, and that is from S, we have a concatenation of two language, S1, S2. It is a concatenation of two languages. Can you hear me? There was some network issue for 1 minute. Yes, can you hear me now?
Yes, sir.
Am I audible?
Yes, sir.
Okay, so do you have any query in this example? This was the last discussion that we have L1 and L2, two languages, and here we have a concatenation of this two languages. So from S, we are generating a rule S1 into S2. So it is showing the concatenation of two different languages, L1 and L2. So now if I want to derive a pattern like A, B, C, C, D, D, so we'll start with S as the first symbol, a starting symbol of the grammar. Now this AB is generated from the L1, and this CCDD will be generated from the another part, that is L2. So I will replace S with S1, S2. We have two options. Now from S1, we'll have A, S1B, S2. We have A, S1B, S2, A, S1B, S2, and then we'll replace this S1 with null. So we'll get A, B, S2. Now from S2, we have C, S2D. So we'll write A, B, C, S2D. And from that, we want one more occurrence of C, again C, S2D and D. And finally, I will replace this with null. So we'll get A, B, C, C, and D, D. So this is how we are able to derive the string A, B, C, C, D, D. This is one example. Now let us derive a string that is only AB. So we can also do that, right? Only AB is also a valid string because we can consider m equal to 0, a special case. If we take m equal to 0, I should able to derive AB. So I will start with S. I will replace with S1, S2. Now from S1 we'll get A, S1B, S2. Now we have AB, S2, and we'll replace S2 with null. So you can get AB. Similarly, if you take n equal to 0, you will get CD as a string. You can also try that example. So I hope this grammar is clear, that how we are generating this grammar, that it is a concatenation of two different languages, L1 and L2. And for L1 we are writing AS1B null. For L2 language we are writing S2 gives CS2D or null. So now in this also we have three non-terminals, that is S, we have S1 and we have S2. We have total 5 rules. The first is S gives S1 into S2. The second rule is S1 gives AS1. Third rule is S1 gives null. Fourth rule is S2 gives CS2D. And fifth rule is S2 gives null. And we have a terminal symbols, that is for A, B, C, D. We have 4 terminal symbols A, B, C, D. So I hope it is clear that how we have generated this context-free grammar. So now let us go to this A raised to N, B raised to M, and M equal to 2N. We have another interesting example here. A raised to N, B raised to M, M equal to 2N. So now let us analyze this pattern first. When N equal to 0, M will be also 0. So we are getting A raised to 0, B raised to 0, that is null. Now when N is equal to 1, we have M will be equal to 2. So it will give us A raised to 1, B raised to 2, which will give us a pattern A double B. When N is equal to 2, M is equal to 4. So A square B raised to 4, which will give us A B B B B. So now if you observe this pattern, we have M equal to 6, we have A cube B raised to 6, we have A, and we have 6 times B. So now from this it is clear that when we are generating one A on the left hand side, we have to generate 2B on the right hand side. And to terminate the process, we have to put null. So if we write a grammar, when we are generating one A on the left hand side, I have to generate 2B on the right hand side. And to terminate the process, we have to put null. So we'll write as ASBB or null. So this will solve the purpose. So now if we want to derive a string, we can start with S. Suppose let us derive this pattern, double A 4 times B. So we'll write ASBB. Then again for S we'll write ASBB. So we have A, then we'll write ASBB, and this last 2B. So finally we'll get the pattern A B B B B, which is our required string. So every time when we are generating one A, we are generating 2B on the other side. So I hope this analysis is clear. Let us proceed further. So, okay, can you suggest me a grammar for this? It is very simple language. You can suggest me a grammar. A raised to N greater than or equal to 0. If anyone can suggest a grammar for this language, A raised to N. Right? If you have a query, you can ask related to this or any another example which we have done. There is no problem. So if you can tell me that what will be the grammar for this, it is very simple language. If you want to analyze, we can analyze like this, that if n equal to 0, a raised to 0, so it will give you null. If n equal to 1, a, so only a is there. If n equal to 2, a square, that is aa. N equal to 3, a cube, so we have triple a. So if you can give me a grammar for this, how we can generate a raised to n. Yes, anyone can unmute and can give me the grammar. For non-terminal s, what we'll write? S can be replaced with
AA and SA.
yes. Can you repeat?
AA and SA.
Okay, so we have two different options here, right? S gives AS or S gives SA, and then we can replace with null. So now these both are correct, right? These are two different options. These are two different options. Either we can write S gives AS or null, or you can write S gives SA or null, because both way you can generate the pattern. So from S, we can write AS. Again, we'll replace S with AS. And finally, we'll replace this S with null to get A square. Similarly, with S, I will write SA. Then for this S, again, I will write SAA. And then I will replace with null. So I will get AA. So you can use any alternative, right? You can use any alternative, any one of them, not both, because both are not required. It is not compulsory. You can use any one alternative and you can generate the answer. So we have two different possible options here. But the example I have taken this has a special reason, that always these two options will not work. Always these two options will not work. So let us understand that with this example, that we have to think wisely which option will work, right? So now let us analyze this. It is a very interesting example. N equal to 0. So we will write 0 less than or equal to m less than or equal to 2 into 0. So again, we will have 0 here. So this will give us 0 because value of m is also 0. So we are getting null. Now when n is equal to 1, we have 0 less than or equal to m less than or equal to 2. So now we have different values of m. You can see it is 0, 1, 2. 0, 1, 2. So that means what? We can get if you compare this, right? The value of m can be between 0, 1, 2. So it can be only a, it can be ab, it can be a double b. Similarly, when I take n equal to 2, we have 0 less than or equal to m less than or equal to 4. So m can be 0, 1, 2, 3, 4. So this will give us AA because n is 2. It is compulsory. Then we have AAB, AABB, AA triple B, and AA 4 times B. So now if you observe this analysis, right, still you can do one more level of analysis to get the exact grammar, but you observe this pattern, then some of the things which are visible, null is generated, so there must be a rule for null. So we can write a rule like this: S gives null. Also there are not two different paths like we have done in the previous example. Also you can see that we have AB, A and B are equal, double A, double B. So this is telling that when we are generating A, we are generating B also. When we are generating 2 times A, we are generating 2 times B. So that is also here. So I can add the rule for that. A, S, B. Now, if you observe this pattern, you can also see that you are generating double B as compared to A. We are generating double B as compared to A. We are generating 1A, we are getting 2B with it. We are generating 2A, we are generating 4B with it. So now, because of that, we have A, S, B, B, which is satisfying this criteria. Now, one more thing is, if you observe this pattern, you will find that you are generating only A, right? So when n is equal to 1, only A is generated. When n is equal to 2, we are generating 2 times A, right? That is important, right? And also we have the special cases which we have to handle. That is this double A and B, double A and triple B. So this is the remaining thing we have to focus on, that we have to generate only A, we have to generate double A B, we have to generate double A triple B. So now let us focus on this 3, right? We have this grammar which we have already written, A, S, B, A, S, double B, or null from the previous slide. This is what we are writing. And now we have to focus on this 3. That is A, double A, double B, if I'm not wrong. Sorry, double A, B. Okay, this is double A, B. And we have one more, double A, triple B. So we have to also focus on that, double A, triple B. Let me check. Yes, this is what we have to do, right? So now, if I consider this pattern first, AAB, right? Let us focus on AAB. So I can say that we are generating A and B, and we have to generate this extra A. Similarly, if I look at this A, B, 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 then I can consider this 1A along with this 2B, because that kind of rule is with me, AS double B, 1A and double B. And then here we have a rule, 1A and 1B. So that means for this pattern, my grammar is sufficient. From S, we'll get AS double B, right? We are generating this AS double B, and now for this S, we'll write ASB, and finally we'll put null. So you can see that we are getting this pattern AA triple B. So we are able to generate this kind of patterns. So we don't have to worry about that. Now here we have this remaining pattern AAB and AA. So now when I am generating this, I have this option to generate only A, right? We have two options with us. S gives SA and S gives AS. Now if I select this option, if I select S gives SA, then what will happen? That we have this kind of derivation. From S we are getting ASB. Now I will replace S with SAB. Now because S is a recursive rule, if I replace with ASB, then what will happen? My string will be AABAB, which is not valid. This is not valid. Why? Because we have to maintain the order. We have to preserve the order. And why this happens? Because we are writing S is equal to SA. This is because we are writing S is equal to SA. So because of this option, you have still a chance to recursively apply S and to get B before the A. You will get a chance to replace S with ASB, and you will have a chance to get B before the A. And here we don't want that. We do not want B before the A because we have to preserve the order of A and B. All the A must be in the beginning and all the B must be at last. So for that reason, here we'll not replace S with SA. We'll not replace S with SA and we'll consider S with AS. So now this will not be a problem. S, then we have ASB. Now I will replace S with ASB. Now if I replace S with one more ASB, still there will not be any problem. Here definitely we can derive our required string AB. If we go for next level, I can have ASB B and we'll get the string AAABB for n equal to 3. For n equal to 3. This is a valid string. Right? So now you can see that the role of S and S gives SA and S gives AS is very crucial. You cannot select any rule randomly. You have to check that by selecting S gives AS or by selecting S gives SA, are we getting a pattern which is not valid? Then by doing that analysis, you have to select the correct rule, whether it is SA or AS. So here we have to add one more rule to complete the grammar, and that is AS. So now our final grammar is this, which will serve the purpose. We can generate any string as per our requirement. Yes, so do you have any query in this example? Because it is a very complex and interesting example. It is a very complex and interesting example. So do you have any query? You want to generate any pattern? If you want to generate any pattern, we can test it also. Okay, so let us proceed. So if we define a context-free grammar, whatever example we have gone through, it has 4 parameters, a set of non-terminals. We have seen that. We have a set of terminal symbols. Always we have a starting symbol of the grammar. And we have a set of production rules. And all the productions, if you have observed, has a form. On the left-hand side, we have a single non-terminal. And on the right-hand side, we have a combination of terminals and non-terminals. So you can see any example which we have gone through. Right? Let us see this. You can see that we have a context-free grammar. We have a non-terminals S, S1, S2, a set of non-terminals. We have a set of terminals which are represented as sigma. Here it is A, B, C, D. We have a starting symbol of the grammar which is S, and we have a set of rules. So that is how we can represent the context-free grammar. And every rule having a criteria that left-hand side has always a single non-terminal. Left-hand side has always a single non-terminal. You will never find any another symbol on the left-hand side. It will be always a single non-terminal. On the right-hand side, we have a combination of both terminals and non-terminals, as we have seen in all these examples. We are writing ASB, so it is a combination of terminals and non-terminals. In some examples, we have written like S gives SS, or we have written S gives S1, S2. So we have a combination of terminals and non-terminals on the right-hand side. So this is how we can have a representation in the context-free grammar. So these 4 parameters are, I think, clear. This is your set of non-terminals. This is your set of terminals, a sigma, a starting symbol of the grammar, and we have a production rule set, that is P. So now let us see other examples. Okay, we have one more equation here. J is equal to I plus K. So I will write as, I will substitute the value of J into this, A raised to I, B raised to I plus K, and C raised to K. So we have this pattern. So now if we write, we'll get A raised to I, B raised to I, then we have B raised to K, C raised to K, where I and K greater than or equal to 0. So now if you observe this language L, it is again a concatenation of two different languages, A raised to I, B raised to I greater than or equal to 0, B raised to K, C raised to K, K greater than or equal to 0. So now for this, we have already written a grammar previously for this kind of language. So for L1, I am using a starting symbol S1. For the L1 language, I will write A S1B or null. For S2 language, I will write B S2C or null. So this is how we'll write for L2 language. S2 is also a non-terminal and starting symbol of the L2 language, and it is a recursive rule. You can apply it any number of times. And to complete the grammar, we write a rule for the concatenation, and we have S1 into S2. And we can derive various strings from this. And we have done this kind of example, but this is a different way to represent the same thing. So I hope it is clear. No need to discuss more because we have discussed this earlier. Okay, now we have one more scenario. Let us have A raised to I, B raised to J, C raised to K. J is greater than I plus K. J is greater than I plus K. So now for this, we'll write A raised to I, now B raised to I plus K plus M, and C raised to K. Here M must be greater than 0 because J is greater than I plus K. So that means if we want to write for J, we have to write I plus K plus some more symbols. It is I plus K plus some more symbols. So now here we have two different ways to solve this example. The first one is we'll write like this: A raised to I, B raised to I. Then we have B raised to K, B raised to M, C raised to K. This is one way to solve this example. Second is, you can see that we are not changing the order of A, B, and C. A raised to I, B raised to I is there. Then we have B, and then last we have C. Now another option is, if we rewrite this, we can also write like this: A raised to I, B raised to I. This you may find more comfortable. Both the way you can solve this. So here we have A raised to I, B raised to I. We have B raised to M, and we have B raised to K, C raised to K. Again, you can see that order of A, B, and C is preserved. Only we are rewriting the above equation. So now, if I consider the second alternative, which is more straightforward, right? Which is more straightforward, then we can say it is a combination of three different languages instead of concatenation of two different languages. Now we have a combination of three different languages. So now let us consider the second alternative, which is more straightforward. So for the first language, L1, here it is L2, here it is L3. So for S1 will write A S1B or null, because I and K can be greater than or equal to 0. For S3 language, we'll write as B S3C or null. And for the S2 language, we want to generate equal number of times B, any number of times B. So we write B S2 because it is B only, no other symbol is there. So we'll write here B S2, and S2 we are not using in any another rule. So we'll write B S2 or B, because M must be greater than 0. M must be greater than 0. So we have to write S2 as B S2 or B. And along with that, we'll add one more rule to complete the concatenation part. And for that purpose, we have a rule which is written as, from S we'll get S1 having a concatenation with S2 having a concatenation with S3. So now we have this complete grammar. Okay, let us derive some string from this. So let us consider the string which is possible in this language. So let us take a string as A, B, B, C, C, right? So you can see J is greater than, okay, so J should be greater than I plus K. So this is not valid. So we cannot derive that. So definitely we have one B extra. And then we have A and B. And we have B and C. This is a valid string where J is greater than I plus K. Also other valid strings we can derive. So let us first derive this. From S we'll write S1, S2, S3 because we require a concatenation of 3. So from S1 we'll derive AS1B. So we'll write as AS1B, and then we have S2, S3. Now we'll put null for this S1. So we have AB, let us consider AB for that. So we have AB, and then we have S2, S3. Now from S2 we'll directly get null B because we require one B. So we have ABB, and we have S3. Now from S3 we'll derive the BC, the remaining part. So we'll write as B S3C, and at last we'll have AB, then we have B, and at last we have BC. We'll put null for S3. So you can see we are getting the string AB, BB, C. This is how we are getting the string AB, BB, C, where J is greater than I plus K. J is greater than I plus K. Let us derive one more string from this, in which we don't have occurrences of all. So I can derive a string like, this is also valid, J is greater than I plus K, where I is 0 here. So we can start with S. We have S1, S2, S3. For S1 we'll put null. We have S2 and S3. Now from S2 we'll write B, and we have S3. From S3 we'll write B, S3C, and finally we'll put null for S3. So we are getting BBC. Similarly, you can generate another string like A double B. So A double B is also a valid string. I is still J is still greater than I plus K. K is 0. So let us derive. We start with S. We have S1, S2, S3. From S1 we'll write A, S1B, S2, S3. We'll replace S1 with null. So we have A, B, then S2, S3. For S2 we'll replace with B, and then last we have S3, for which we'll put null. So we are able to get the string ABB, in which also J is greater than I plus K. So I hope you are getting this example. It is very interesting. Okay, now if it is clear, if we have I is equal to J plus K, but J and K greater than or equal to 1, right? I is equal to J plus K, where J and K greater than or equal to 1. We need some modification in the previous grammar. So if we write the grammar for this, it is like this: A raised to I, B raised to I plus K. Sorry, it is I is equal to J plus K this time. So I have to replace the value of I. So it is A raised to J plus K, B raised to J, C raised to K. And for this we'll write A raised to J, A raised to K, B raised to J, C raised to K. So further, if we rearrange this, because both J must be together, so we have to rewrite this: A raised to K, A raised to J, B raised to J, and C raised to K. So now here you can see the group. A and C are together, and once you generate A and C equal number of times, you have to generate B and C equal number of times inside A and C. So once you recursively generate A and C, then you have to go to next level, and then you have to generate equal number of times A and B. Then it will be sufficient. So now to achieve this goal, right? So if we derive any string so that you can understand the grammar, let us have this string A, B, C, where I is equal to J plus K. So now if you observe this pattern, it is something like this, that you have to derive A and C, then inside that you have to derive A and B. Then it will be I is equal to J plus K. So now what we'll do, first we'll generate A and C. We'll generate A and C. So now for that we'll write from S, I will get A, S, C. It is a recursive rule, so I can generate and apply that rule any number of times. A, C, and once I'm done with generating A and C equal number of times, I have to generate A and B inside it. So I will replace S with non-terminal A. I will replace this non-terminal with non-terminal A. Okay, now if I replace A with small a, capital A, B, and AB, because J and K is greater than or equal to 1. So then we are able to derive some strings, but some modification is still required. Let us see first that what strings we can derive from this. So we'll start with S. Let us generate this string A, B, C. We'll start with S. We have A, S, C. So we'll get A and C. Then I will replace capital S with capital A because my requirement of A and C is over. This I have already done. Now I want to generate A and B, but this A and B is inside AC. So now I will replace capital S with capital A, and then for capital A, we'll write A, small a, capital A, B, and C. Now, if I write like this, it will create a problem because we don't have null here. J and K greater than or equal to 1. So now, what we'll do, we'll directly put the value of AB here. So capital A is replaced with AB directly with the second alternative, and we'll get the pattern as AABC. So it is telling that J and K greater than or equal to 1. Now let us take another string. Let us take another string in which both must be there. So now only problem here is if I consider this grammar, then from S I can directly go with non-terminal A. This I can replace with A, B. Then again I will replace with AB. So it is generating a pattern AABB, because what is the rule that J and K both must be greater than or equal to 1. Both must be greater than or equal to 1. That means we must have K present. We must have occurrences of K present in it. So when we are generating K, automatically when we are generating C, which is representing your K, we have to generate also A, because A and C are equal always. A raised to K, C raised to K, right? Because A raised to K, C raised to K is there. So we have to slightly modify this rule, and what we'll write, we'll replace S with definitely ASC, and also we'll replace with A, capital AC. So now what will happen? This will never allow you to generate the pattern which is not in the language. So you cannot generate AABB. Now you cannot generate a pattern AABB. So now what is the advantage? Now suppose you want to derive the string AABC. Now you want only one occurrence of A and C. You want only one occurrence of A and C. So now for that purpose, we have to start with S. Because we want one occurrence of A and C, we'll not use the recursive part. We'll not use the recursive part, and we'll replace S with small a, capital A, C. And now for this capital A, we'll replace with AB. So we have small a, then we'll replace capital A with AB, and we'll put C. So we are getting the string AABC. So you can see that if we want one occurrence of A and C, if we want one occurrence of A and C, we'll replace S directly with small a, capital A, small c. If we want more occurrence of A and C, right, then we have to use ASC as a recursive rule. So here if I modify this string, let us append one more A and C. Same modification will be done here. I have to write like this, S, then we have ASC. So this will give us A, C, and A and C. You can see now I am getting the new string. So when I want more than one occurrence of A and C, right? If I want to generate K more than once, when K is more than once, I have to consider in this way. I have to first apply a recursive rule. S gives ASC. Then when I want the last occurrence of A and C, then I will replace S with small a, capital A, small c, and then we'll get the answer. I hope this example is clear. Any query in this? Because it is a very complex example. So if you have any query, you can ask me that why we have done like this. Yes, are you getting this? Yes, can we proceed further? Or if you want to derive any string, if you want to check any another string, we can do that also. Okay, let us see one more interesting pattern. I hope there are no queries in this. So we have I equal to j or j equal to k. So it is again a different kind of example. So let me explain. We have two languages here, a raised to I, where I equal to j. So I can replace j with I. And at that time when I is equal to j, there is no rule for k. So k can be anything. We have another language, a raised to I, b raised to j, c raised to j. Now here I can be anything. So we have two different types of strings which are varied in this language. When a and b are equal or b and c are equal. Either a and b are equal or b and c are equal. So now if I consider the L1 language, for the L1 language where a and b are equal and we can have any occurrence of c. So again we can say this L1 is nothing but it is a concatenation of two different languages. Your L1 language is again a concatenation of two different languages. We can say L11 and L12 because you can see it is a concatenation of a raised to I, b raised to I with c raised to k. So if I write L11, my L11 will be equal to a raised to I, b raised to I, and L12 is c raised to k. It is a concatenation of two different languages because c raised to k is independent. So it is a separate language. A raised to I, b raised to I, it is another language. So now we have to write like this, that for L11, I will write a grammar as S11, which will give me A, S11B or null, because there is nothing is specified for I. Only I is equal to J is given. So I can be null also. 0 also. When I is 0, definitely J will be also 0. So for A raised to I, B raised to I, we'll write like this. For L12, we'll write S12, a recursive rule. Now it is C raised to K. Also it is at the last position, so we'll write CS12 or null. So it is for the C raised to K. We can generate independently C any number of times. Now our L1 language is a concatenation of these two languages. So for L1, we'll take a starting symbol of the grammar as S1 and we'll write S11 into S12. We'll write as S11 into S12. So this is for L1 language only. Now similar to that we have to write for the L2 language. So now let us analyze the L2. It is A raised to I, B raised to J, C raised to J. So for L2 we'll write A raised to I, B raised to J, C raised to J. So again this L2 is having a combination of two languages. A raised to I, it is independent, and B raised to J, C raised to J. So we can say it is L21, L22. So for L21 we'll write S21, which is we are generating A any number of times. So we can write AS21 or null. This will generate independently A's. Then for S22, which is for the language L22, we'll write BS22C or null. So we are generating B and C equal number of times, BS22C or null. Now again L2 is a concatenation of two different languages. So we'll write S2 for L2 language and we'll write S21 into S22. We'll write S21 into S22. So now this is for the L2 language, but our language is not L2, our language is not L1, our language is L. Our actual language is the language L. So which L is nothing but union of two different languages. It is a union of two different languages, L1 and L2. So now what we'll write, to achieve the goal, we'll write one more rule, S, which is for the language L. It is a union of two different languages, S1 or S2. And here we'll add the rule for your reference. For S1, which is your previous one, S11, S12. For S11, we'll write AS11B or null. For S12, we'll write CS12 or null. So now we can say this is your complete grammar. This will be the complete grammar. Having S gives S1 or S2. S1 is for the I equal to J. As you can see here, this is representing your I equal to J. And this one, S2, it is representing J equal to K. So also from the grammar itself, you can see I equal to J. So A and B are equal. You can see A and B are equal. From this, J equal to K. So you can see that B and C are equal. And we are generating independently A. So this is what you can easily observe, that I equal to J. So A and B will be equal. And independently we are generating the C. When J is equal to K, we are having B and C equal, and we are generating independently A. So you can see that how many non-terminals we have in this grammar. Can anyone identify number of non-terminals? Count. How many non-terminals we have? Yes. If anyone can tell, how many non-terminals we have in this grammar? Yes, anyone can give. I think it is a very simple, straightforward question. How many non-terminal symbols we have used? Yes. Yes.
Six.
Or not, your voice is not clear. Number of non-terminals in this grammar. So only one student can give the answer? No, I'm sure many students can give the answer. Yes, anyone else? Yes, we have non-terminal S. Let us circle it. Then S1, second, third, fourth, fifth one, sixth, and seven. These seven are non-terminals because for each non-terminal we have a rule. We have a rule for each non-terminal. We can replace S, we can replace S1, we can replace S11, we can replace S12, we can replace S2, we can replace S21, we can replace S22. So these are all non-terminals of this grammar. We have three terminal symbols, A, B, and C in this language, and we have several production rules. Can you tell how many production rules we have? How many rules we have in this grammar? Total rules in this grammar. Yes, can anyone tell? There are total 13 rules, 13 rules in this grammar. Okay, so let us take a similar example. A raised to I, B raised to J, C raised to K I equal to j or I equal to k. That is I equal to j or I equal to k. So let us analyze this because this is similar to previous one. So we'll solve quickly. We have again two languages. L1, which is a raised to I, b raised to I, c raised to k. We have L2 language, which is a raised to I, b raised to j, c raised to I. Again, for L1 language, we have two languages, a raised to I, b raised to I, and we have c raised to k. And for this L2, you can see a and c are equal. Inside that, we have to generate b. Inside that, we have to generate b. So now for the L1 language, if we generate, it is a combination of two. So we can write like this: S1 gives S11, S12. From S11, we'll get equal number of times A and B. So this is what we have done previously. It is similar to that, no change, I equal to j part. Right? We have concatenation of two different languages, A raised to I, B raised to I, and C raised to K. So we can directly write like this. And now for L2 language. For L2, we have to take S2. Now from S2, we'll get A S2C. So we'll generate equal number of times A and C. Then I will replace that with any another symbol. Right? So I am taking any non-terminal. And for this, we can independently generate B. And finally, we can write S gives S1 or S2. So either you can select S1 to generate A raised to I, B raised to I, C raised to K, or you can generate from S2 A raised to I, B raised to J, and C raised to I, where A and C are equal. So now let us derive one string which is of the another type, From S we have S2. Let us take this A, B, C, C. We are considering I equal to K. So from S we'll get S2. From S2 we'll get A, S2C. We'll repeat the same rule. A, S2C. We'll get AA and CC. Now to generate B, I will replace S2 with capital B. And then finally, for capital B, we'll write AA, small b, capital B, small c, 2 times. And then we'll put null at last. So we'll get the pattern AABCC, which is our required pattern. This is how you can generate a complete grammar for this language: A raised to I, B raised to J, C raised to K, I equal to J, or I equal to K. Okay, let us take one more example which is different from this. Let us have I plus J is equal to P plus Q. We have I plus J equal to P plus Q. So now we have various options here. When you consider this, this is a valid option A. When we generate one A, we have to generate one D. So again, I plus J will be equal to P plus Q. When I generate one A, I can generate one C, which is a valid option. When I generate one B, I can generate D. When I generate one B, I can generate C. So if I consider this combination A, B, C, D, it is something like this: A and D, B and C. If I consider A, B, C, D, D, then A is generating D, then A is generating D, and then B and C. Similarly, I can consider A, B, C, C, D. This is also valid. A and D. Then inside it we have A and C, and at last we have B and C. So these are some of the options. One more option we can consider: A, B, C, D, D. So you can see A and D we can generate, then B and D, and inside that we have B and C. So these are all valid options, right? So outermost is always A and D, then we have B and C, or which is the innermost one always. So innermost level is indicating that we have always B and C. No other combination is possible at the inner level, whatever example you will consider. And outermost level is also fixed. It is A and D. You can skip any level, but the outermost will be A and D. If you skip outermost level, the next can be either A and C, or it can be B and D. Anything is possible, right? At the next level, if you skip A and D. So now when you want to write a grammar, you have to check this all different cases, and then the innermost level is your B and C, and outermost level is your A and C. So let us first put the outermost level. So for outermost level, we'll write ASD, that is the outermost one. Then the innermost one is B and C. So I can take any symbol. Suppose let us say capital C for that. And we'll write B, capital C, small c, or null. So this is the outermost level. S gives ASD. The innermost level is C gives small b, capital C, small c, and null. Now we have other levels like A and C should be together, as you can see here. A and C should be together, and B and C should be together, as you can see here. So now for that we'll write A as a non-terminal. Now A and C should be together. So we'll write small a, capital A, small c. Now once you are generating A and C, still you can generate B and C inside it. As you can see here, you are generating A and C, but still inside it you can generate B and C. It is a valid combination. So because still B and C is a valid combination, which is generated from capital C, we'll write the alternative as capital C here. Now another is, let us consider a non-terminal B. Now we are generating B and D, another combination, small b, capital B and D. Also you can see in this slide that when you are generating B and D, at that time still B and C is a valid combination inside it. When you are generating B and D, still B and C is a valid combination inside it. So because of that, we'll put capital C here also. So you can generate B and C inside B and D. So I hope you are getting my point, that inside B and D you can generate B and C. Inside A and C you can generate B and C, but you are never able to generate B and D inside A and C. You can see once you generate A and C, you cannot have B and D inside it. Once you generate A and C, you cannot have B and D inside it, because D is the last one. So it cannot be inside A and C. So that's why we don't have to worry about that. So either BC will work, or AC will work, but A and B will not be there. Now, along with this ASD, I told that if the outermost level is not there, if outermost level is also not there, then this combination is also a valid combination. B, B, C, D. This is also a valid combination. B and D, right? B and D is a valid combination, and inside which we can generate B and C. So to achieve that goal, here I will put B. So we'll get B and D. Similar to that, this is also a valid combination. A, B, C, C. A and C. Outermost level is not there. Outermost level is not there. But we directly have AC. We are skipping the AD level. We are skipping the AD level. Still, I plus J is equal to P plus Q. So now to achieve that goal, we are adding in this capital A. So now, if you look at the final grammar, this will be the final grammar, right? Where S gives ASD or B or A. B and A are capital symbols here, non-terminals. Then A gives small a, capital SE or capital C. Capital B gives small b, capital B, small d or capital C. And capital C gives small b, capital C, small c. Let us derive one string A, B, C, C. So we'll start with S. Now A and C we have. So directly I will replace S with A, which will give me A, C. Now inside that we want B, C. So I will replace this capital A with C. And from C we'll get A, B, capital C, small c, and C. And we'll get A, B, C, C. This is how we can derive this string. Similarly, if we want to derive another string, we can derive that string like A, B, C, D. Let us have this. So we'll start with S. We'll replace with A, S, D. So we got A and D. Now we'll replace S with B, C. So directly from S, we can select either A or B, anything. So I will select here B. From B, I will directly go to capital C, and then we'll get B, C, C, and D. So we'll get A, B, C, D. So you can see here that we are getting this solution also, A, B, C, D. And similarly, you can try different strings. Okay, now this context-free grammar generation is a process where there is no end. It is an endless process. There are so many different variations and so many examples. So we have to put some limit over it, that when to stop, because it is an infinite process. So we have covered most of the varieties of the context-free grammar that will help you to understand the other examples which are given in the book as well as on the internet. But make sure that you verify your grammar by yourself, because many solutions on the internet are not correct. So be careful. Don't accept all the solutions directly. Check by yourself, generate various strings from it, and then use that grammar. So you can see that we have discussed about a context-free grammar which we can generate for different context-free languages. And also we have defined the definition of a context-free grammar, that what is the representation of a context-free grammar. On the left-hand side, we have a non-terminal. On the right-hand side, we have a combination of terminals plus non-terminals, as we have seen in the previous slide. So with this, I end this session. I hope you have enjoyed this session and you have learned how to generate a different context-free grammar for different context-free languages. Thank you. So if you have any query, you can ask me. I hope you have enjoyed this session also. Thank you.
Thank you, sir. Students, if you have any doubt, then please ask. You have time now. Thank you, sir. You have explained very different examples in detail. Thank you very much, sir. सारे एग्जांपल्स हमें काम में आएंगे सर. अभी सेशन रिकॉर्ड करके रखा है फर्दर ऑल्सो. थैंक यू वेरी मच सर. थैंक यू.
Thank you, Charuset, and all the team members who were involved directly and indirectly in this event. Thank you all.
थैंक यू सर.